Hello, good day. My name is Mr. Modulus. Today we are going to consider physics. So our favorite topic today is dimension. So um, let's get started. All right. So what is dimension? The term dimension simply means the single aspect of something. It can also be seen as the measure of the spatial extent. The spatial we're talking about here is pertaining to space. The spatial extent in a particular direction, like height, width, and length. What do we mean by dimension in physics? Basically, dimension in physics is the property of a physical quantity which demonstrates the fundamental measure of that very physical quantity. In other words, dimension is a term in physics used to describe the fundamental measurement of a particular quantity, or it is the property of an object, the property of a quantity that shows its fundamental measurements. In this context, we are going to use the three most important fundamental quantities to analyze other quantities, such as mass, length, and time. Moreover, in physics, we have two kinds of quantity. We have the fundamental and we have the derived, whereby the derived quantities are defined as the combination of the same or different fundamental quantities. Meanwhile, we have seven important fundamental quantities, which are time, length, mass, amount of substance, temperature, electric current, and luminous intensity. Okay, so among these seven, the three most important is mass, time, and length. Why are they most important? They are most important simply because most of the quantity, which are the derived quantity, depends on them. So today, in dimension, any quantity that cannot be measured in the unit of these three most important fundamental quantity has no definition in dimension, such as length, time, and mass. And any quantity, however, which can be measured in unit of length is said to have a dimension of length. And any quantity which can be measured in unit of time is said to have a dimension of time. And any quantity which can be measured in units of mass is said to have a dimension of mass. So we are going to be using the first capital letter of time, mass, and length to denote their respective quantity. Okay, so mass will be denoted by capital M. Length will be denoted by capital L, while time will be denoted by capital T. Of course. Now, there is what we call the SI unit, the System International Unit. It is the basic unit, the fundamental unit used by physicists in the various components, in the various parts of the continent to measure problems. All right, to measure quantities in a problems. All right, so this XI, which is System International Unit, is initially called kilogram meter seconds units. So it's initially called kilogram meter second units, whereby kilogram is the SI unit of mass, denoted by capital M, and meter is the SI unit of length, denoted by capital L, and seconds is the SI unit of time, denoted by capital T. So if I bring the two of them together, three of them together, we have MLT. So this will be the standard form of any quantity in this context, because the definition of the dimension of any quantity lies within these three. So any one that cannot be measured in any of these units has no definition in dimension, right? So now I just showed you the symbolic representation of each of the quantity. Now let's go into their dimension. Of course, dimension of mass, we can denote it as dim mass. Dimension of mass, we can denote it as dim mass. Could be represented by, so the dim here represents dimension. So dimension of mass, dim mass, could be represented by, this is mass already, so represented by a capital, a parenthesis. A parenthesis. So this parenthesis is a symbol of the dimension. So a parenthesis, then mass will be inside it. So this is the dimension of mass. However, dimension of length, which is dim length, can as well be represented by a parenthesis having a capital L inside it. And dimension of time, which is dim time, also have capital T, parenthesis, closing capital T. So you see that the parenthesis here, the square parenthesis or the rectangular parenthesis here, is a symbol of dimension, right? Whereby the symbols here represent their respective quantity, all right? So these are the three possible quantity that will be seen in dimensions, right? So, and this is their standard format, the kilogram meter second unit, which is the initial definition of the SI unit, the System International Unit. All right. So now, how do we now transform this into this form, MLT? So how do we transform this into MLT? Of course, we can do that. Okay, we start from this one. So the dimension of mass, which is dim mass. In this case, when we look at this, we see we have M here, so we have M, but we have no L and T. So how do we bring L and T in this equation, in this system? The only way to do that is, without altering the magnitude of M, is to use the principle of indices. In indices, anything multiplied by 1 is that thing, and this is anything raised to power 0 is 1. So you see that if we can introduce ones here, 1 multiplication by 1 here doesn't change the amount. Then how did this one play a very important role in this context? Of course, there is a way we can introduce this thing which is going to be equivalent to 1, and we will achieve our target. How do I mean? According to indices, anything raised to power 0 is 1. So if I bring L raised to power 0 is still 1. 1 times M is still M. And also bring T raised to power 0 is still 1. And therefore 1 times M is still M. So we will just introduce L here as L raised to power 0 and T here as T raised to power 0. You know, if we are to calculate this in mathematics, it's going to be M times L raised to power 0 is 1, T raised to power 0 is 1. So of course, 1 times 1 is 1, then 1 times M is still M. So you see, you are still correct. So the logic we just did here, the logic behind all this, in fact, the wisdom behind all this is to introduce L and T, and in such a way that we will not alter the magnitude of M. So we still have M at the end of the day. So this is the standard form of the dimension of mass. So we are going to use this intelligence to evaluate the remaining two, which are dimension of length. So here we have dimension of length, so which is dim length. Dimension of length, dim length, which is so if we follow the format MLT, so we have no, in dimension of length we only have length, so we have no M, so therefore M we introduce as raised to power 0. Then we have L there in dimension of length, and we have no T in dimension of length, so T will be introduced as to the power of 0. All right, so we try the remaining, which is time. So we have dimension of time, which is dim time. Dim time. So here we have only t. So every other thing will be introduced as raised to power 0. So we have m raised to power 0, l raised to power 0, t. All right. So this can be also regarded as the dimension of mass, length, and time, respectively. Just this is equivalent to this. We just have to put it in a form of MLT. I mean, in a form of MLT. That is the standard form of the of quantity, the standard representation of quantity in dimension. All right. So now we are going to consider dimension of some of quantities, precisely derived quantity. Okay, so example. Find the dimension of the following quantities. So number one, we have area. I we have volume. I we have density. We have density. IV, we have speed or velocity. V, we have acceleration. Acceleration. VI, we have force. VII, we have work done. VIII, we have pressure. I have pressure. Then IX, we have momentum. X, we have impulse. XI, we have okay, momentum, impulse. Okay, we can add okay, let's call it okay, I'm coming. I have III, XIII, we have gravitational constant. Gravitational constant. Okay, XI, let us include power and so forth. So gravitational constant, capital G. Gravitational constant, capital G. So we are going to find the dimension of this important quantity. Now remember that any quantity that can be measured in units of length has a dimension of length, and any quantity that can be measured in units of mass has a dimension of mass, and any quantity that can be measured in units of time has a dimension of time. Any quantity that cannot be measured in any of these three units, these three important fundamental quantity, has no dimension within the scope of this topic under O-level physics, because we are considering O-level physics in a moment of time. Okay, so let's get started. Solution. So remember, we'll be using DIM as a symbol of dimension, right? So if I see dim anything, any quantity is dimension of that quantity, okay? So now we start from the first one, which is, before then, we're going to define the definition. We define it first, all right? So for we to find the dimension of any of the quantity, we define the quantity first. Then we can now find the dimension. All right, so let's go. So area by definition is length times width. Now remember that length is still length and width is also a shorter length. So here we are not interested in the size, we are interested in the originality of the quantity. So both of them are still length. though the width is the shorter length. All right, so we can now define area as length times length. Okay, so this can be extended as area can be extended as length times length. All right, so therefore we have the dimension of length, which is dimension of area, sorry, which is dim area, should be dimension of this length multiplied by dimension of this length, which is dim length multiplied by dim length. All right, so in that case, what is dimension of length? Of course, dimension of length is capital L. So we have capital L within a parenthesis multiplied by another capital L within a parenthesis. So here we apply mathematical principles. So we open the bracket. So this should be, okay, let's open the bracket here. This should be L times L. All right. So if you open the brackets, we have L times L because there is a multiplication operation between the two L. So L times L is L squared, right? Yes, L squared. When quantities are multiplying, their power is being altered. Their power increases or decreases depending on the nature of the power, all right? But when they are dividing, also their power increases or decreases depending on the nature of the power as well. But when they are adding or subtracting, their coefficient is what is altered. So here the power is altered. So we have L squared. So that should be the dimension of the area. So therefore, dim area is L squared within parentheses. So we'll go back to the next one. So we start with dim volume. Okay, first of all, we define it. So have volume. So volume is length times width times height. Of course, like we did in the area, both length, width, and height, all of them are length. So we are not interested in the size, we are not interested in the pattern, we are only interested in the originality of the quantity. So the originality of the quantity is that all of them bears the name length. All of them are length. However they appear, all of them are length. So we can see that as length times length times length, all right? So we have that this is length times length times length. So therefore, dimension of volume, which is dim volume, is going to be dimension of this length, which is dim length, multiplied by dimension of the second length, which is dim length again, and multiply by dimension of the third length, which is dim length. So at the end of the day, we now have, okay, before I forgot, if we go back to this under area, you know that we put the standard form as MLT. So this can as well be put in a standard form. We only have L there, which is L squared. So we have no M and T in this. So we can introduce M and T by giving them power 0 so that it will not affect the magnitude or the size of L squared. So we can write this as M raised to power 0, then L raised to power 2, then T raised to power 0. So I hope you understand, because why M power 0, T power 0? The answer is very simple. There is no M and there is no T. So the power 0 denote that there does not exist in that quantity, but we are just trying to introduce them. We're just trying to make them visible, all right? So they do not exist here. So that's why that is the essence of the power 0. Because M power 0 is 1, T power 0 is 1. 1 times L squared, L squared. 1 times L squared, L squared. So this is also equivalent to L squared. Okay, so let's go there. So here we have the dim length here is capital L multiplied by another dim length, which is another capital L, multiply another dim length, which is another capital L. So at the end of the day, we have L times L. Okay, we open the parentheses, open the bracket. So if we open the parentheses here, we have L, capital L times capital L times capital L. So we have 3 L multiplying each other, which is L cube, right? So L cube, meaning that L multiplies 3 times. So the power, the number of times the quantity multiply itself. So it multiplies itself 3 times. All right. If you want to understand more, if this is not more clear to you, you have to go into my videos on mathematics on how to do some simple simplification of algebras, multiplications, additions, subtraction, and all of them. Okay. Thank you very much. So that is it. Now, how do we put this in a standard form? Okay. The standard form should be, so remember the pattern is MLT. So we have no M here. We have no M in this quantity, so we introduce it as power 0. So we have L cube already. So we have L cube. And we have no T here, so we have to introduce it as power 0. Okay? So that should be the standard form of dimension of volume. All right, we'll go back to the next one, which is density. So we have I. So density. So we define density. By definition, density is mass over volume. So density tells you how massive an object is, how massive a quantity is. Okay, that's by the way. Now, what's the dimension of density? So therefore, dimension of density, which is dim density, will be defined as the dimension of mass because it has mass. So we have dimension of mass divided by dimension of volume, which is dim volume. Okay, so what is dimension of mass? Of course, dimension of mass is capital M in parentheses. And what is dimension of volume? Of course, dimension of volume is capital L cube. Okay, capital L cube. Like here, capital L cube. Now, so therefore, we have that dimension. Okay, let's continue. So this will be equals to, of course, anything that divides, according to law of indices, 1 over x raised to power n is x raised to power minus n. That is the 1 over here. The 1 over here makes the power of x, which is n, to be negative. So anything, any quantity that has a negative power, it means that the quantity is at the denominator of a fraction together with the power. So the negative insinuates 1 over. It means 1 over, right? So if this should be 1 over, 1 over x raised to power n should be x raised to power negative n. So the negative there is this 1 over, right? Is this 1 over. If I can extend it, if you have a over b raised to power r, of course this should be a times 1 over b raised to power r. Of course, a times 1 is a. We can do this over 1. A times 1 is a. Then 1 times b raised to power r is b raised to power r. So by this definition, so 1 over b raised to power r is b raised to power negative r. So this should be a over 1 is a, then times, okay? So this should be a times, because a over 1 is a, then this 1 over b raised to power r is b raised to power negative r. So what I'm trying to explain here is that whenever a quantity is at the denominator of a fraction, if you want to explain that quantity in a separate way, as in form of multiplication, the power must carry negative. All right, the negative shows that it is its position is at the denominator of a fraction. So because that this L here is at the denominator, because this is a fraction now, M over L cube, because that this L is at the denominator of a fraction, this L cube is at the denominator, so the power must carry negative as a multiplication, showing that the negative shows that it is at the denominator of a fraction. All right, so now we are going to write this as M times L raised to power minus 3. Okay, so the negative is the reason of it being at the denominator of a fraction. So if I fail to put this negative, that means this L raised to power 3 is not considered at the denominator, rather at the what? Numerator. So the negative shows that it is positioned at the denominator of the fraction. So to understand more about this, you're going to watch my videos on simplification of algebras, addition, multiplication, and all that. All right, so that will give you a clear understanding. Thank you. Okay. So here, if we do the multiplication, we'll be having that this is ml raised to power negative 3. Okay, so that should be our final answer, but we need to put it in a standard form, in form of mlt. Okay, we already have m here, we already have l, so this should be m l raised to power negative 3. Then there is no t, so we introduce t as power 0. So anyone that carries power 0 means that it does not exist there in the quantity, all right? But we're just trying to put them in a standard format whereby the 3 possible quantities found in dimensions will be present, all right? So anyone that carries power 0 does not exist in that very quantity. Thank you. Now we go over to the next one. Speed or velocity. Speed or velocity. So here we have speed, speed or velocity. They means the same, right? That's why I position them together. Speed or velocity means the same. It's just that this one has to do with direction. This one has no direction. This one is the direction is not important here. In fact, velocity, speed. Okay, velocity is is a speed that has a direction, right? It's a speed that has a direction. So both of them have the same unit because both of them is defined as change in length with time. All right. By definition, speed is the rate of change of distance with time, while velocity is the rate of change of displacement with time. Of course, distance and displacement are the same. It's just that displacement is a distance that travels in a particular direction. In other words, displacement is a distance that has a direction. So if I should define it, speed by definition should be distance, and velocity by definition should be displacement. So all over time, time is what they have in common. So distance is for speed, displacement is for velocity. Now to show you that both of them are the same, distance and displacement are still the same thing, all right? It's just that displacement is a distance that has a direction, all right? So that is why we now have what is called vector and scalar. So we use these two terms to differentiate quantities that has direction and the one that has no direction. The vector quantities are those quantities that has both magnitude and direction, while the scalar quantities are those quantities that has only magnitude but no direction. And velocity has both magnitude and direction, which makes it a vector, while speed has only magnitude but no direction, which makes it a scalar. So what that differentiates both of them is that velocity is a vector and speed is a scalar. If we ignore direction, both of them are exactly the same. All right. So the direction part of speed is velocity. That is the explanation. So whether displacement or distance, or whether distance or displacement, both of them means one thing: length. All right. So we can use length to replace any of them. All right. That's why I put them together, because they are the same thing. So therefore, they will have the same dimension. All right. So that is it. So we have IV. So this will be equals to length over time. Length over time. Okay. So therefore, dimension of, let's use velocity in this case. So dimension of velocity. So the velocity is replacing both itself and speed because they are the same. Should now be the dimension of length over dimension of time. So this is dim length all over dim time. Right? And dim length already is capital L in parentheses, and dim time is capital T in parentheses. Okay, so at this point we have L over T. Of course, according to indices, anything that has no power, the power is 1. All right, so we don't need to put it like this, we need to bring them together. we need to express them as a multiplication because MLT is in form of multiplication. MLT is in multiplication form. So we are going to put them in that multiplication form. So how do we do that? Of course, I told you that whenever you see any quantity or any quantity at all at the denominator of a fraction, you can introduce it as a multiplication as a negative power. So whatever that is the power, you should attach negative to it. So here the power is 1, so we attach negative to that quantity. Remember, in indices, anything that has no power, the power is 1. So someone will ask, where did I bring this power? Of course, I've said it before, and I'll say it again and over again. So the power 1 is as a result of this having no power. So it means that this t is multiplying itself only once. So that is it. That's why you see that t is something as 10 raised to the power 1, 10 is something as 10 raised to the power 1, and so forth. So this can be written as L times. So because this is at the denominator of the fraction L over t, so it's going to be t raised to power negative 1. So the negative shows that the t raised to power 1 is at the denominator of the fraction. So the negative shows that it's at the denominator. It is 1 over. All right? So that is it. So we close the parenthesis. So at the end of the day, we now have that this will be equals to LT raised to power negative 1. So I have LT raised to power negative 1. Right? So bring them together. Okay, so, but we're not going to leave it like this. This is the final answer anyways. But to put it in this form, MLT. So we only have L and T. They are here, but M is not there. So the one that is not there, we introduce it as raised to power 0. So we have M raised to power 0, L, then T raised to power negative 1. So that is the dimension of velocity. So we'll go back to the next one, which is force. So we have, that should be our V. We have force. Of course, by definition, force is mass. Okay, sorry. We'll go back to acceleration. Acceleration. The next one is acceleration. Okay, so acceleration is defined as change in velocity. Okay, change in velocity with time, over time. So change in velocity is also a velocity, right? Change in velocity is a new velocity, and velocity is velocity. So which is velocity over time. Okay, so therefore dim acceleration, therefore dimension of acceleration will be equals to dimension of velocity over dimension of time, because acceleration was defined in terms of velocity and time. So therefore it must have a dimension of velocity and a dimension of time. So we have, this is dim velocity over dim time. Okay, so in the end we have that dim velocity. So what is dimension of velocity? We already did it here as LT raised to power minus 1. So we have LT raised to power negative 1, and all over dimension of time is capital T. All right, so in the end we can express this as LT raised to power minus 1. These two are together, they multiply. Remember, we are going to express denominator as a multiplication. So multiply, because it is at the denominator. Of course, anything that has no power, the power must be 1, right? Why I introduce this power is because I want to bring out the negative. So the negative is meaningless if there is no power here. So we need to have a power so that when we're attaching the negative, it will be meaningful, right? So now we put this as a multiplication, which is t raised to power 1. But because that this came from the denominator of the fraction, we attach negative. All right, so this is t raised to power negative 1. Okay, so we close the quantity. So we introduce the parentheses. So now these we put the parentheses. So this will now be equals to, of course, we have two t's here having power negative 1, negative 1. According to law of indices, a raised to power m times a raised to power n, provided they have the same base, of course, the multiplication become addition to their power. So we take one of the base and add their power, which is m plus n, which is m plus n. So here we have t raised to the power minus 1 times another t raised to the power minus 1. So we add the two power. So we take one of the common base, then we have negative 1 plus another negative 1. So which is automatically t raised to the power negative 1. Of course, plus times minus is minus. Of course, negative 1 is negative 2. You are owing 1 and you are owing 1. Altogether, you are owing 2. So we have 2 t raised to the power minus 2. So this will now be lt raised to the power negative 2. Of course, that is the dimension of acceleration. But I'll put it in the standard form, in form of mlt. We only have L and T, but with no M. So we can introduce M here. Because M does not exist in this quantity, so we can introduce it as raised to power 0. So we have M raised to power 0, then we have L, then T raised to power negative 2. And that is the dimension of acceleration. Now we go over to the next one. So the next one is force. So we have VI. So we have force. So by definition, force is mass times acceleration. So mass times acceleration. So therefore, dimension of force, which is deemed force, is equals to, because force is expressed in terms of mass and acceleration, therefore, dimension of force must have a dimension of mass and a dimension of acceleration. So we have dim mass multiplied by dim acceleration, which is dimension of acceleration. Right? So in the end, dimension of mass is capital M. Why parenthesis with capital M, why dimension of acceleration is parenthesis with LT raised to power minus 2. So I have LT raised to power minus 2. Alright? So if we open bracket, it's going to be MLT raised to power minus 2. And this is already in this form, MLT. So there's no need of introducing anything. Everything there is present already. So we'll go back to the next one, which is work done. Work done, VII. So have work done. Of course, by definition, work done is force times distance. Force times distance, that is work done. Of course, which can be also extended as force times, of course, distance is length. So in this context, distance means length. So this is force times length. So therefore, dimension of work done should be dimension of force multiplied by dimension of length, because for work done is expressed as force and length, so therefore it must have their respective dimensions. All right, so we have that this will be equals to dimension of force is already mlt raised to the power minus 2. So we have mlt raised to the power minus 2, then multiply by dimension of length is capital L. So now we open bracket, so we multiply everything. So we have mlt raised to the power minus 2 times L. Because we have L here already, so L times L should be L squared. So we have 2L. 2L multiply itself because multiplication operation exists in between them. So L times itself is L squared. So here we'll be having ml squared coming from L times L, then remaining t raised to the power minus 2. Of course, this is the standard form because it already contains MLT. So we have MLT there. So this is the dimension of work done. So we'll go back to the next one, which is pressure. So have VII. So the eighth one, so have pressure. So by definition, pressure is force on a unit area. force over area by definition. So therefore, I'm going to borrow here. So therefore, dimension of pressure, which is Dym pressure, will now be dimension of force, which is Dym force, all over dimension of area, which is Dym area. All right, dimension of area, which is Dym area. So which is now equals to, of course, dimension of force is already mLT raised to power minus 2. So have mLT raised to power minus 2 in parentheses over dimension of area is already L square, because area is length times length, right? And length times length is length square. So now we have two lengths multiplying each other here, which is L square. L square means L times L. We have only one length here. Of course, if I should break this thing more down, it should look like this. mLT raised to power minus 2 in parentheses all over L square is L times L. All right, that's what it means. Somebody will ask, why do I break it down? Of course, I want to explain what I want to do right now. You can do it in many ways, all right? You can do it using indices and all that, but I just want to do it this way. So L, we cancel one L. So remaining one L at denominator, which I can simply give it power 1, all right? So we have mT raised to power minus 2 and L. So this will be equals to mT raised to power minus 2. Then we have another remaining L. So if we introduce it as a multiplication, the power is going to carry negative, all right? So it's going to be L raised to power negative 1. You know, the negative is because it is at the denominator of the what? Fraction. MT raised to power minus 2 and what over what? L. Okay? So if we bring them together, of course, we are going to put them in the order MLT. So after M, we have L before T. So this, okay, let's put the parentheses. So this is going to be mT raised to power negative 1, then T raised to power negative 2. So that is the dimension of pressure. All right. So we'll go over to the next one. So the next one is power. Power. So we have, that should be my IX. IX. So we have power. Of course, by definition, power is time rate of doing work. So which is work done over time. Work done over time. So therefore, dimension of power, which is Dym power, should be dimension of work done, which is Dym work done. You can also call it work, right? Work done is something as work. It's just that we want to make it more standardized. That's why we put it work done, right? So all over dimension of time, which is Dym time. Okay, dimension of work done, we have already explained it here as mL square T raised to power negative 2, right? So let's do that. So we have this will be mL square T raised to power negative 2. That is dimension of work done all over dimension of time, which is T raised to power negative 1. Which is, dimension of time, which is T, capital T, right? Okay, so now to express this as a multiplication, to express this T here as a multiplication, we have to give it power here 1, so that because the power is going to carry negative, so we need to introduce the power here. So this is going to be this multiplied by T raised to power negative 1 as usual. So this is going to be equals to mL square T raised to power negative 2 multiplied by T raised to power negative 1. I hope you know where this is coming from. From here, the negative is as a result of this being at the denominator. To explain that this T raised to power 1 is coming from the denominator, we need to put a negative power, all right? So a negative. sign, negative sign to the power. So that is it. So if we bring this together, so we're having ml square. Of course, we apply indices here. They have the same t. All right. So let's do it somewhere here. The same t. Once there is multiplication, it will be addition to their power. So we take any of the t here as our common t. So we add their powers, which is -2 plus -1. Okay. So which is equals to t raised to power -2. Of course, plus times minus is minus. So I have -1. Of course, if you are owing 2 and you are owing 1, altogether you are owing 3. So this is t raised to power -3. So this is -3. So therefore, the dimension of power is ml squared t raised to power -1. Remember, it goes by the format mlt, kilogram meter seconds. That is the old SI unit, old name for SI unit, the System International Unit. Okay, so we go back to the next one, which is number 10, impulse or momentum, anyone. So we have momentum. Of course, by definition, momentum is mass times velocity. Mass times velocity. Now, I want you to know that momentum and impulse are the same because it takes impulse to create change in momentum. In fact, it takes impulse to create momentum. Impulse is a force or a blow given to a body and the time of action of that force. And momentum is the tendency of a body in motion to resist an external force. So for a body to begin to move, the body needs an impulse. And any body in motion has a momentum because the momentum of a body is defined with two quantities: the mass of the body, which is the body itself, and the velocity of the body, which is the speed or motion of the body. So anybody that has no speed has no momentum, and anybody that has no mass has no momentum. All right. So you now see that for a body to begin to move, the body needs an impulse. That is a force that will be exerted on it and the time of action of that force. And whenever a force is exerted on a body, the body is given an what? Impulse. So that's why I say it takes an impulse to create momentum. So impulse is equivalent to momentum. So which means that we are meant to have the same dimension. So they are meant to have the same dimension. So if we solve for dimension of momentum and impulse and they are not the same, that means something is wrong somewhere because they are equivalent in terms of fundamental measurement. They are equivalent. Impulse and momentum are equivalent. So let's go there. So we have so therefore we have a dimension of momentum, which is d momentum, is equal to dimension of mass, which is d mass, multiplied by dimension of velocity, which is d velocity. All right. So therefore we have that d momentum. Okay, no need. So we have this will be equals to what's dimension of mass should be capital M, multiplied by dimension of velocity should be capital LT raised to power -1, because that should be length over time, right? Yes, displacement over time. Okay, so if we bring them together, it's going to be okay, let's open the bracket. If we open the bracket, it's going to be M times L times T raised to power -1. Okay, so we bring them together, we now have that this will be equals to MLT raised to power -1. So that should be the dimension of momentum, MLT raised to power -1. So how about impulse? What SI? Let's talk about impulse. Of course, impulse by definition is force times time. So the force exerted on the body and the time of action of the force. So therefore, dimension of impulse, which is d impulse, should be equals to, because impulse is defined in terms of force and time, so therefore it's going to be dimension of force Dimension of force times dimension of time. Okay, so what is dimension of force? Of course, we already know that dimension of force is mLT raised to power minus 2. So which is mLT raised to power minus 2, then multiply by capital T, which is dimension of time. So if we bring them together, if we open the brackets, we're having mLT raised to power minus 2, then times capital T, right? Times capital T. So if we bring them together, remember, anything that has no power, the power is 1. So if we bring them together, we'll be having, okay, let's do it here. We're having mLT raised to power minus 2 plus, all right, plus 1. Because they have the same, they are multiplying, so we add their power. We take one of the common base, then we add their powers. Minus 2 plus 1, you are owing 2 and you have 1. Of course, you'll be owing 1. So minus 2 plus 1 is minus 1. So this, therefore, which will be, so therefore we have that dimension of impulse will now be mL T raised to power minus 1. mL T raised to power minus 1, which is also the same thing as the dimension of momentum. All right? The same thing as dimension of momentum, mL T raised to power minus 1. So you see that both of them have the same fundamental measurement, all right? Because they are equivalent. They are almost the same. It takes momentum, it takes impulse to create momentum, or it takes impulse to create change in momentum, which is also momentum. All right, so let's go to the last but not the least, which is the dimension of the gravitational constant, right? The gravitational constant. Okay, which is number 12, II. So first of all, let us go and establish gravitational constant. Of course, gravitational constant came from the law governing the force between two masses. According to Sir Isaac Newton, he says that if two bodies, let's call their mass M1 and M2, experience a force F, he says that the force is proportional to the product of the masses, which is M1, M2, and inversely proportional to the distance between the two. So assuming that the 2 has a distance d, of course, okay, let me use here M1. So we have M1 here and we have M2 here. Okay, let me write it bold so that it can be clear. So we have M1 here and we have M2 here. So he says, according to Newton, that they experience a force between them. And if d is the distance between them, that they experience a force, F. This force acts on the line joining the center of the two masses. That this force that the two of them experience, according to Newton's law of gravitation, is proportional. This F is proportional to the product of the two masses and inversely proportional to the, inversely is over, all right? A denominator inversely proportional to the square of the distance, so d square, of course. So to bring equality, because that a quantity varies as another does not mean they are equal. So to bring equality between them, we need to introduce a constant, and that constant they introduced here is the gravitational constant, which is capital G, right? So we have F equals to capital G M1 M2 over d square. So that is where the gravitational constant comes into play, all right? So if we define it, so we can say, so from here, if we make G the subject of the formula, so if we make G the subject of the formula, here we have let's do it somewhere here. If we cross multiply 1 times g m1 m2, so it's going to be g m1 m2, okay, equals to f times d square f d square. So we divide both sides by m1 m2. So you can, if you don't understand this, watch my videos on change of subject or formula in mathematics. All right, so we have, if we divide both sides by m1 m2, so we have that g will be equals to f d square over m1 m2. So that should be the formula for gravitational constant. So gravitational constant is force times distance squared times mass times also another mass. Okay, so we have two distances multiplying each other and two masses also multiplying each other, but these masses are different where the distance are the same. Okay, so we have that the capital G. So here we have capital G, which is gravitational constant, is equals to f d square all over m1 m2. So it doesn't matter, even if we have different masses, the dimension remains the same, because so far it is mass. The original name is what we are looking for, the original quantity. We are not looking at the size, we are looking at the originality, which is the mass. So whether we have different masses, it's still the mass. So when we come to dimension, different masses are represented as just a mass. So each of them can be called mass. So let's go. So therefore, we have that dimension of gravitational constant, which is dimension of capital G, should be dimension of force multiplied by dimension of distance squared multiplied by dimension of this and dimension of that. So we have dimension of force F multiplied by dimension of D square over dimension of the first mass M1 multiplied by dimension of the second mass. Okay, let's use multiplication operation. Multiply by dimension of the second mass M2. So this is going to be equals to, because dimension of force, we have already defined it as mlt raised to power minus 2, right? That is dimension of force, times distance is a length, of course. So here we have length square. So dimension of length square should be capital L square, because the dimension of length is already L. But here we're not just dealing with one length, but we're dealing with square of the length. So that's why we have the square. So this square is as a result of this, all right? So all over dimension of the mass is capital M. Okay? Capital M times another capital M. Okay? So of course from here, mass can cancel mass. Yeah? And this will be equals to L times L. L times L square, because they are multiplying. So it's going to be L t raised to power minus 2 times L square, then all over capital M. So which will be equals to L times L is L cube. L cube, of course, this is power 1. If you add there, if you take one of the common base L, you add their power. 1 plus 2 is 3. So we have times t raised to power minus 2, then multiply by, this one has no power, so the power is 1. So multiply by, because it's a denominator, the power will carry negative. So we have negative 1. All right? Okay. So at this point, this will be equals to, let's put in alphabetical order. In the order of the SI unit. So we have kilogram, which is mass, meter, which is length, seconds, which is time. So MLT. So we have M, which is M raised to power minus 1, L cube, and T raised to power negative 2. So that is dimension of gravitational constant. So therefore, the dimension of gravitational constant G is equals to M negative 1 L cube and t raised to power minus 2. So that is it. So any other further questions you need to ask, you can comment on the comment section. You can write it up on the comment section, and it will be our pleasure to answer you. Thank you and God bless you. So in a nutshell, dimension is a term in physics used to describe or used to explain the actual measurement, or the fundamental measurement of a physical quantity. Meanwhile, it is the property of a physical quantity which is regarded as the fundamental measurement of that quantity. And we also say that any quantity which can be measured in units of length is said to have a dimension of length. Any quantity which can be measured in unit of mass is said to have a dimension of mass. And any quantity which can be measured in unit of time is said to have a dimension of time. And we also concluded that any quantity that cannot be measured in any of these three quantities, which are length, time, and mass, which are the three most important fundamental quantity, does not have a definition in dimension, because the only existing quantity in dimension is length, time, and mass. That is the only existing quantities in dimension. The only quantities that has a definition in dimension. So therefore, for we to define any quantity, we must find a way to express them in terms of time, length, and mass. Either combination of any of them or all of them. All right? So except them, we have no definition for dimension of any quantity. At this point, do have a good day.